this video we are going to discuss about some important topics for your exams. But before that, let me introduce you some important definitions and their examples. So first one is neighborhood of a point. This is a little bit different from metric space. In a metric space, XD, an open ball BDXR centered at X and with radius R is typically said to be a neighborhood of the point X. But in case of topological spaces, this doesn't work out. In case of topological space, X tau, let X be any point of X. Then a set Nx containing the point X is said to be a neighborhood of X if there exists an open set OX. Since it is open, it must belong to tau. Since tau is the complete list of all open sets of X. So if there exists an open set OX in tau such that X belongs to OX, which is a subset of Nx, then Nx is said to be a neighborhood of the point X. Now, neighborhood system. Neighborhood system means the set of all neighborhood Nx, such that Nx is a neighborhood of X. This set is said to be a neighborhood system and is denoted by scripted Nx. Now, neighborhood base. Neighborhood base means, let us denote neighborhood base as Px. Neighborhood base is a subset of the scripted Nx, such that for any neighborhood Nx in the neighborhood system Nx, there must exist some P in Px such that X belongs to P, which is a subset of Nx. This is said to be, then the set Px is said to be the neighborhood base. That is, for every neighborhood in the neighborhood system Nx, there must exist a subset P contained in this set. Then the set Px will be called neighborhood base of that system. Now let us take some examples. Neighborhood of cofinite topology. I have already discussed what a cofinite topology is in my previous video, and also said that cofinite topology is very much important for your exams. So for cofinite topology, let X tau be a topological space where tau is cofinite topology and X be real number set. So if X be any point lying in capital X, how will a neighborhood of this point look like? Since any open set lying in tau looks like the whole real number excepting some finite number of points. So any open set, what I mean to say is any open set of this topology tau will look like the whole real line excepting these finite number of points. Okay, so now for any neighborhood X, since any neighborhood Nx of X, since Nx belongs to tau, so Nx will also look like this type of set. That means Nx will also look like a real line excepting some finite number of points. So this is the structure of a neighborhood for cofinite topology, so that we can write x minus nx is some finite number of points a1, a2 up to some an. Next topic is first and second countable spaces. Let x tau be a topological space. Then it will be called a first countable space if first countable if for each point x in x the neighborhood system nx has a countable basis base, and it is called second countable if the topology T has a countable base. Okay, so what are the difference between these two? If a topology has a countable base, that means if a topology is second countable, then it is also first countable. But if a topology is first countable, it does not have to be second countable. So let us take an example for that. Let x be real number set and tau be discrete topology. Okay, I've already discussed about discrete topology, which is the power set of x. Okay, now if we take the neighborhood base for any point, say x belonging to x, the base of the neighborhood system for x will be like the singleton x. Since the singleton x is contained in every neighborhood nx of x, so this is base of the neighborhood has only element this singleton, but this is not a second countable space. Why? Because tau itself contains uncountably many elements. Why? Since R has uncountably many subsets. Okay, so there will be uncountably many uncountably many elements in the base for this topology. So that is why tau has no countable base, but for each neighborhood, for each x, the neighborhood has a countable base. Okay, so this is an important example as well. Now let us solve some questions. First, a 2 marks question says, is the intersection of infinite number of open sets open in a topological space? Justify. Okay, intersection of infinite number of open sets may or may not be open. Let us take an example. Let x tau be a topological space such that x is R and tau be the standard topology. Okay, standard topology. Then if we consider the set this minus 1 over n to 1 over n, where n belongs to natural number, then intersection of all gn will be what? Only 0, singleton 0. Is it open or not? No. Since this is singleton, there is no such element in tau. So this is not open. So in this case, intersection of infinite number of open sets is not open. But let us take x tau, where x and tau are the same. Okay, x is equal to r and tau is standard topology. And let us take Gn as minus n to n. N belongs to natural number. Then G1 is what? Minus 1 to 1. G2 is minus 2 to 2. And so on. So now intersection of all these elements will be what? Intersection n belongs to natural number. Gn will be minus 1 to 1, which is open. So intersection of all open sets may or may not be open. And the second part of this question says, also give an example of a topological space where any intersection of open sets is open. So for the second part, we have to give an example where any intersection of open sets is open. Let us take x be real number and the topology is indiscrete topology. The topology is discrete topology. Discrete topology. Okay. So we can choose any family of open sets. Okay, which is not defined right here. Any family of open sets where n belongs to some countable or uncountable set lambda. Okay, now intersection of any collection of open sets here is again a subset which is take S is again a subset of X, so it must belong to tau. Since tau is discrete topology, so tau contains all the subsets of X, and intersection of these all elements is again a subset of X, so it is contained in tau. And since it is contained in tau, this means S is an open set. So intersection of any open sets is open in this case. Our next question is again for 2 marks, which says, show that the lower limit topology on R is not second countable. I have already discussed what a lower limit topology is in my first video. So now we have to show that any base of the topology tau. Okay, let us first take x tau be the lower limit topology on R, where x is R and tau is lower limit topology. Then we have to show that any base of R, any base of T is uncountable. Okay, so now if possible let x tau, let tau has a countable basis. Countable base. We are assuming this. So for any set that belongs to tau, there must be an element countable. Let us consider the base. Let us take the base b. Okay, so for any element in tau, there must be an element b1 in the set B, such that for all x belongs to AB, which is contained in B1. For all x belongs to AB, x is contained in B1, which is subset of AB. Okay, now we are choosing x is equal to A. Okay, so if x is equal to A, then there must exist some C which will belong to A to B, which will belong to open A to open B. That I mean to say, if I choose some x is equal to, if I choose x as A, then there must exist some C such that x will be contained in AC, which is subset of AB. Okay, now this one is a basis element. Now since this set AB can be since this interval AB can be chosen uncountably many ways. Why? Because A can be rational or irrational. A can be rational or irrational. So if A belongs to Q, then A must be A must be chosen countably many ways. But if A belongs to R minus Q, then A can be chosen uncountably many ways. So in that case, we cannot find a countable basis, since for each selection of X, there must be at least one interval containing X. So you have to write this logic and then say that this is how the basis cannot be countable. Okay, since the set of irrationals is uncountable, hence the basis is uncountable, so T is second countable. Okay, the next question says, prove that in a topological space Xt, if G and H are open sets, then interior of G intersection H whole bar is equal to interior of G bar intersection H bar. Further, if G is open and H is dense, that means dense in X, then G intersection H whole bar is equal to G bar. This is a 6 marks question. So, for the first part, we know that for any set G and H, G intersection H is a subset of G. So, G intersection H whole bar is a subset of G bar. Also, G intersection H is a subset of H, which implies that G intersection H whole bar is a subset of H bar. Therefore, combining these two, we will get G intersection H whole bar is a subset of G bar intersection H bar, and since this is a subset of this one, so we can conclude that interior of G intersection H whole bar is a subset of interior of G bar intersection H bar. So this is number 1. And now conversely we take, to prove the other side, we will take, let X belongs to interior of G bar intersection H bar. Okay, and since X belongs to interior of some set, then there must exist a neighborhood Nx of X such that X belongs to Nx, which is totally contained in G bar intersection H bar. Okay, since the neighborhood Nx of X is totally contained in G bar intersection H bar, so we can conclude, since G and H both are open sets, so we can conclude that there must exist another neighborhood Nx dashed and Nx double dashed of X such that X belongs to Nx dashed is a subset of G, and X belongs to Nx double dashed is a subset of H, since these two are open. Okay, Hence, x belongs to nx dashed intersection nx double dashed is a subset of G intersection H, which is a subset of G intersection H whole bar. Any set is contained in its closure. Also, since these two are open sets, so intersection of these two is also an open set, and X is contained in that open set, and this open set is contained in this set. So that means X is an interior point of this set, right? So X belongs to interior of G intersection H whole bar. And this proves interior of G bar intersection H bar is a subset of interior of G intersection H whole bar. Okay, and we name it and we denote it as number 2. So from 1 and 2 we can say that interior of G intersection H whole bar is equal to interior of G bar intersection H bar. Okay, now for the second part. It is given that G is open and H is dense. G is open and H is dense in X. Dense in X means H bar is equal to X. And also there is a property, take that as a note, that if any set is dense in X, then intersection of that set with any open set in X is never empty. That means if OX be any open set in X, since OX is open set, it must belong to tau. Okay, so for any open set OX intersection H is not equal to phi. Why this happens? Because H is dense in X. So this is the property of dense sets. Now G intersection H is a subset of G. So G intersection H whole bar is a subset of G bar, right? So we name it as equation 1. Conversely, let X belongs to G bar. Okay, so then for any open neighborhood Nx of X, can we say that Nx intersection G is not equal to phi? Why so? Because X belongs to G bar. That means X belongs to either G or X belongs to G dashed, that is derived set of G. If X belongs to G, since G is open set, so this neighborhood is totally contained in G for any neighborhood. Okay, so this neighborhood has some points of G. Okay, and if X belongs to G dashed, then it is totally clear from the definition of limit point. Okay, so we can conclude in either case Nx intersection G is non-empty. Now since Nx and G both are open, this is neighborhood of X, so it must be open, right? Since Nx and G both are open, so Nx intersection G is also open. And since this one is open, so its intersection with H is not equal to phi. Why? Because of this property, and H is dense. So Nx intersection G intersection H is not equal to phi. And this proves what? X belongs to G intersection H whole bar. So we can conclude that G bar is a subset of G intersection H whole bar. And from 1 and 2, we can conclude that G intersection H whole bar is equal to G bar when G is open and H is dense. So that is it for today, and if you want more solutions in an easier way, then don't forget to like, share, comment and subscribe. Thank you.